All right, so hopefully you've gotten a chance to try 7A on 5.9 or worksheet 16.4. What I'm going to do now is walk through it, and then I'm going to also walk through one more problem from worksheet 16.4, and then I'll give you a chance to try a few more problems. You can check your work from the answer key, and then I'm going to do one more short lecture to get you able to do worksheet 5.10 as well. So in 7A, the question is asking is at what temp will the following process be spontaneous? So again, I'm looking for my temperature in this reaction, and this is the equation I'm obviously using, but I've rearranged to solve for T. And again, I'm trying to figure out T at equilibrium. So at equilibrium, delta G is 0, okay, or this variable right here is 0. So I'm rearranging the equation to solve for T when delta G is 0. And what that equation looks like is this right here, all right? So to solve for T, I plug in my delta H, I plug in my delta S. Now to make sure my units match up, here's kind of the trick, and hopefully you caught it. If not, again, that's why we're practicing. And the trick is you need to make sure your units line up. So in this case, delta H is in kilojoules, delta S is in joules. So I need to make them both the same. Typically, I convert kilojoules to joules simply by moving the decimal 3 places or just adding 3 zeros, same thing. So my delta H is 18,000 joules. I divide that by my delta S, which is negative 60 joules per Kelvin. What ends up happening is I get 3 times 10 to the second kelvins, or 300 kelvins. So this is the temperature. This is the temperature at which I'm at equilibrium. So I need to ask myself, above or below this, is my reaction going to become spontaneous? So for that, I look at delta H and delta S. So in this case, delta H is negative, it favors. Delta S is negative, it does not favor. So I want this section to be small, okay, because delta H favors, delta S does not. So for this section to be small, I want low temps. So at any temp below 300 Kelvin, this process will be spontaneous, or delta G will be negative. And that should be your answer, and that should allow you to do kind of a lot of the problems from this worksheet, as long as we understand how to use this new equation that we derived, this equation right here, that we derived from this equation up here. Okay, this equation up here. All right? All right, so hopefully that went well. If not, hopefully we understand where we went wrong. Next, let's look at question number 8. So question number 8, a little spin on the equation that we have been using. Let's read through the problem, then I'll kind of go over what exactly it's asking. Ethane thiol is commonly added to natural gas to provide the rotten egg smell of a gas leak. The boiling point of ethane thiol is 35 degrees Celsius, and its heat of vaporization is 27.5 kilojoules per mole. What is the entropy of vaporization? So the question is asking, what is the entropy? Well, what variable is entropy? Remember, entropy, again, is S, okay? So we're looking for delta S here. What is the entropy of vaporization for the substance? Its heat of vaporization, okay? Its heat of vaporization is how much energy does it take for it to vaporize, okay? Or that is also delta H, okay, or change in energy. So heat of vaporization, delta H, we're looking for delta S, and here is my temperature, okay? So I am going to, again, say at the boiling point, delta G is 0. So I'm going to use this equation right here, delta H equals T, delta S, but I'm again looking for, or excuse me, in this case, I'm looking for entropy. I'm looking for delta S, not T like I have been. So I rearranged the equation a little bit differently. I divided T over. Okay, so now I have delta S equals delta H over T. My delta H is 27.5 kilojoules per mole. My temperature is 35 Celsius. So hopefully, again, we remember that Celsius needs to be converted to Kelvin. Okay, in this unit, our temperature in this equation is kelvins. So I'm going to add 273 to that, and I'm going to put my delta H right on top. Okay, so I take kilojoules per mole, 27.5, divided by 273 plus 35, and I end up getting this. Okay, 8.93 times 10 to the negative second, or 0.0893 kilojoules per Kelvin times mole is my unit for delta S. So in this case, I calculated my entropy of vaporization. If I wanted to put that in joules, okay, I don't know, this question didn't ask me to, but if I wanted to, it'd be 89.3 joules per Kelvin times mole. And that's my answer. All right? So what I would like you to do now is take a few minutes, but keep in mind, I do want you to watch one more video. Take a few minutes and practice some of the questions from 16.4. Check your answers. Make sure you kind of grasp that equation, delta H equals delta H minus T delta S, and this equation right here that we got from rearranging or understanding that at equilibrium delta G is 0. So take a few minutes, work on 5.9, worksheet 16.4, and then I am going to have you watch one more video to get you ready for worksheet 5.10. So hopefully that helps.